Hi, boys and girls. All right, we've got another graph to do. This one is from Nick's walk, where he started at the 8 meter card. He walked back to the 0 meter card near the refrigerator, and then went back to the 8 meter card near the sliding glass door. Because there's a lot of data, just like in our last video on Friday, I went ahead and created the coordinates for you, and by turning my data table that we did when we first collected the data, I turned it into coordinates by just simply copying them down very neatly, and then also remember putting the comma and the parentheses around them. Keep in mind that time is always represented on the x-axis, and you always do the time first. So when you're plotting coordinates, you just go the number to the right of the first number first, and then for the second number is the number that you go up on the y-axis. All right, please keep in mind a couple of things about graphs. Graphs always have a title to tell you the main idea of what they're about. Remember, the whole idea of a graph is for you to be able to take a very complicated set of data like this and be able to make some sense out of it at just a glance. Like if I look at this, I've gotten pretty good at it over time, so I can see that here Nick was traveling like half. He was traveling, only taking half a second to travel 1 meter for like this amount of time, because it's 4.55, 5.5. But it's going to be way easier to just look at the slope on the graph and see where it gets steep to know where he's speeding up, and where it gets flatter to know where he's slowing down. The graph makes it easy to just spot the trends once you understand what the trends look like. All right, so let's get to the graphing. The first point that we have to do is 0 time. No time had passed, and Nick was starting at the 8 meter card. At 0 time passed, before I started the timer, Nick was standing at the 8 meter card. All right, next, 1-7. When 1 second had passed, Nick was at the 7 meter card. When 2 seconds had passed, he was at the 6 meter card. When 3 seconds had passed, he was at the 5 minute card, or 5 meter card, sorry, not minute. All right, now 3.5 seconds. So I have to go in between the 3 and the 4. And at 3.5, he was at the 4 meter card. So he sped up just a little. All right, and then 4 meter card, 4 seconds, he was at the 3 meter card. So it gets a little steeper right here. All right, and then at 4.5 seconds, he was at the 2 meter card. So 4.5 and 2. He got a little faster there too. All right, and then at the 5 second mark, he was back to 1 meter. Right, and at 5.5, he was at 0. So it makes a pretty steep slope at the beginning. Now, as you recall, Nick started out at the sliding door at the 8 meter card, and then he walked really fast back to the 0 meter card by the refrigerator. And you can see a pretty steep slope forming there. But when Nick turned around, he started to go slower. Now, let's see. Let's go down. So we were at 5.5. All right. At 7 seconds, he was at 1 meter. And then at 9 seconds, he was at 2 meters. See how the dots also spread out from each other? See how close the points are to each other to make that steep slope? And now as soon as we see where Nick was slowing down, you can see how the points spread apart from each other. All right, we were at the 9. All right, let's do it. 10 seconds, he was at 3 meters. At 12 seconds, he was at 4 meters. All right, at 14 seconds, he was at 5 meters. Again, notice that the points are further from each other. All right, Then at 16 seconds, he was at 6 meters. And then at 17 seconds, he was at 7 meters. And at 19 seconds, he was at 8 meters. So if we go back and make a diagonal, I'll make it a little more perfect than it actually is by just connecting the distance and the ending time for that walk. So on Nick's walk from the door back to the refrigerator, he did that in 5.5 seconds, which is a pretty steep slope. And then on the walk back to the sliding glass door from the refrigerator, I tried to keep it as constant as possible, but it's hard to get it perfectly constant. All right, but then you can see that it's not nearly as steep on the way back. So again, on the first part of Nick's walk, it was a fast constant, or as constant as we could get it. And that is very steep. And on the way back to the sliding glass door, it was a slow constant, or at least we attempted to be constant, which is less steep. Now, I also want you to notice that both this walk and the last one from Friday show a change in direction. And I want you to compare and contrast the way the graphs look, right? If you were going to notice what's the same about them, I would notice that they both have lines that come to a point, right? When you're heading from the home point or the 0 point, then you make like the top of a tent or the top of a house when you return. If you start away from home, come back to home, and then go back out, then you make a V. So it's either an upside down V or a V, but that V shape indicates any time that you have a change in direction. Now, some graphs, right, if you go forward and back and forward and back, they can go up and down and up and down and up and down for as long as you run the time, which is what is happening when you have a heart monitor. The time can go on for as long as you're monitoring the heart, and it'll have increase and decrease of heart beating, right? So this could look like this, but what you're really seeing is someone move away and back, away and back, away and back, just like Nick did, right? In fact, we could even we couldn't hook these ones up, but right? No, because I did them backwards. But you could have another part that goes back and then just keep on going. And it would just look kind of like a very pointy roller coaster. But every time you have this point, that's a change in direction. Now, I wonder if you remember from the definition of acceleration that acceleration is a change in velocity, which means it's a change in speed or in direction. So, weirdly enough, when you have a little v on a distance over time graph, you have a change in direction, right? Which is also acceleration. In this graph, you would have acceleration right here because it's a change in direction. Now, other places on this graph that you would have acceleration would be right here because you're going from no speed to moving. So that's a change in speed, right? Right here would be a change in speed. Oh, that's speed. And then right here, when Nick stopped, was another change in speed. Now, when you're looking at the graph, we were trying to keep it constant. Do you see that? But Nick really didn't. So any place that the diagonal isn't perfect would have been a slight change in speed, or else it would have been a mistake with me collecting the data. Does that kind of make sense? Over here, if we had been able to perfectly capture from this time, from this distance to this time, right, we'd have a perfect diagonal, but Nick was slowing up and speeding down, speeding up and slowing down a little bit, or else I was collecting the data a little bit wrong. So any of those little bumps or jags inside of the diagonal would actually be a slight amount of acceleration because it's a slight change in speed throughout his walk. But it's very hard to have a perfectly constant speed, especially if you're a person traveling. So keep in mind that a there and back kind of graph is a change in direction, and changes in direction looks like V's or upside down V's. All right, that's it for today. Good job, my friends.